For the last few weeks we have been studying what happens when we add thermal energy or subtract thermal energy to matter. And really we started this by looking all the way back at an ideal gas and the ideal gas law, PV equals nRT. And this relates the temperature of a substance, of a gas, to its pressure and its volume. Now in a gas, there's considered to be no potential energy between the particles because they hit each other and bounce away from each other. There is no force of attraction. So it turns out that the temperature of a gas is directly related to kinetic energy. So temperature is actually a direct correlation to kinetic energy. So when we add energy to a gas, we can change the pressure and volume. And that's sort of a thermodynamic process. We also know that we can add heat to something, and the amount of heat added or lost is equal to the mass times the specific heat times the change in temperature. And if we add heat and the temperature doesn't change, then we must be going through a phase change. And so we have Q equals M times L, the latent heat. And this could be the latent heat of fusion or the latent heat of vaporization. Either way, all of these processes involve adding or removing energy to the system. And really, thermodynamics is all about that. And the first law of thermodynamics tries to explain what happens when we add heat to a system. So first law of thermodynamics. Now, there's some sign convention here that we're going to need to be familiar with. Dynamics. And there's an equation that you need to be familiar with. But you're already familiar with the equation. The first law of thermodynamics just says energy is conserved. Okay? The difference between this and the other time was we've looked at the law of conservation of energy is we've usually only looked at mechanical energy, kinetic energy, and potential energy. But this time we're going to look at also internal energy. Now internal energy is given the symbol U, and so the change in internal energy of a system is equal to the heat added to the system minus the work done by the system. So the sign convention says this: heat is considered positive if it's added to system. Okay? So if you imagine taking, I don't know, a chamber of air, it's closed at the top, and you light a fire underneath of it, you are adding heat to the system because this system is this thing. And so that's going to increase the internal energy of the system. Now, if you were to put this over a bunch of ice cubes and heat were to flow this way, then you would be taking energy out of the system. And in that case, the Q is negative. So this is heat removed. So this is heat added if it's positive. This is heat removed if it's negative. The work thing is a little bit weird, right? So how do you do work, or how does a system do work? Well, the work is positive if the work is done by the system. If work is done by the system. Okay, now how does a system do work? Well, imagine that this box is actually a cylinder, and up here this is a piston that can move back and forth in it. So if we added a little bit of heat to this thing, then that might cause the gas pressure to go up, which might actually push this piston. And remember, work is equal to force times distance. So when this thing exerted a force to push it through a distance, the system did work on the object. Since it did work to raise this thing up, it transferred energy from itself, from the system, to this piston, and therefore the energy went down. So when the work is done by the system, we consider the work positive, but when you add or subtract a positive, it's going to take energy out. Now, conversely, there's negative work if work is done on the system. So imagine instead that somebody were to push down this piston. Well, then they're exerting a force on all these particles of gas through a distance, and so work is done on this. That's going to make these things collide with their walls more often, and that's either going to cause an increase in pressure or an increase in temperature. It's going to increase the thermal, or not the thermal or internal energy of the system. So internal energy, thermal energy, they're the same thing. Now, this is incomplete because this describes this pretty well, but we can have systems that are actually in motion and have kinetic energy, and systems that have potential energy. So all we have to do is include those in the law. So it turns out that the change in kinetic energy of a system plus the change in potential energy of a system plus the change in internal energy of a system is equal to the heat gained or lost by the system minus the work done by the system. Now this equation is going to be pretty important later when or make more sense, I guess, maybe when we're talking about heat engines and how we get engines to actually do work. They convert thermal energy into useful mechanical work. But let's just take a look at an example problem. So imagine that a 3-gram bullet hits a tree moving at 400 meters per second and exits at 200 meters per second. Now, what I want to know is what happened to the kinetic energy that was lost, and well, okay, let's just answer that question. What happened to lost kinetic energy? Now, since the bullet was at a constant height, we can say that the change in potential energy, I'll write that here, the change in potential energy is zero. We're not really gaining or losing potential energy as the bullet moves through the tree. The heat gained and the work done. Well, what we have to do is we have to figure out what our system is. Okay, is our system the bullet? Is the system the tree and the bullet? Now, if we take our system to be the tree and the bullet, then what we have is no potential energy involved and no work is done by or on the system. Now think about that. If the tree and the bullet is our system, then work has to be done by an external force. But these two things are here together. So if the bullet and the tree are together, then there's no external forces acting. Now if we take just the bullet to be our system, which we can do, then there is work done on the bullet. Okay? And actually a couple things are going to happen. Work is done on the bullet to slow it down, but its temperature is also going to increase. But if we take both things together to be our system, then there can't be any work done because all the forces are internal. So the work is also zero. So this leads us to the change in kinetic energy plus the change in internal energy is equal to zero, which just basically means the change in internal energy is equal to the negative of the change in kinetic energy. Well, it's easy to find the negative of the change in kinetic energy. So final minus initials, so we have 1/2 the mass of the bullet times the final velocity squared minus the initial velocity squared, or 1/2 0.003, because that's got to be in kilograms, times 400 squared minus 200 squared, and this works out to be about 180 joules negative, final 200, 400, had those backwards. This works out to be about negative 180 joules, so we get the negative of the change. The change in internal energy of the system is equal to 180 joules. What does that mean? That probably means that the temperature of both of these things increased. Okay? They gained some internal energy. Now, if we considered the bullet alone as our system, work would have been done on it and the heat transfer would have occurred as well. But since we took the two together, the work done is zero, and so basically all we had happen was kinetic energy transfer into internal energy, so the particles in both of these things are moving a little bit faster, so the tree got a little bit warmer, the bullet got a little bit warmer. That's all that happened.